Good morning. Welcome to the second keynote of the day with Dr. Chuck EASTTOM. Dr. EASTTOM holds a Doctor of Science in Cybersecurity PhD research papers so far, as well as a senior member of both IEEE and ACM. Currently, Dr. EASTTOM is an adjunct professor for both Georgetown University and the University of Dallas. Today, he's speaking on the impact of machine learning on cybersecurity. Dr. EASTTOM, thank you so much for joining us today, and I will go ahead and turn it over to you.
It's my pleasure to be here. Machine learning and cybersecurity are both two topics that capture everyone's attention. How much is real? How much is hype? And exactly what is really going on in the world of machine learning with cybersecurity, both defensively and offensively. A lot of people focus just on the defense, but there are offensive uses as well. Well, first, I wanted to bring out a few very recent news stories. This one came from just a few days ago in Forbes magazine. They had an article, What Machine Learning Can Bring to Cybersecurity. Now, the fact that it's in Forbes magazine tells me that this is becoming a very mainstream topic. Frankly, Forbes is for business leaders, people of that sort of profession. So what we're seeing is the C-level executives are now setting up and paying attention to both machine learning and cybersecurity. Now, in this article, they focus primarily on defensive measures, things like recognizing threats, using data science to analyze data, that sort of thing. There are also a few papers, all published within the last year at most, which talk about supervised machine learning, using machine learning to defend against SCADA industrial control systems, using machine learning to detect zero-day threats. All of these are new research papers. What this tells you is that there are scientists involved in cutting-edge research to advance these areas. Now, what we're going to do today is first give you a brief overview of machine learning and AI in general, because I find a number of people have misunderstandings. And then we're going to move into the specific applications to cybersecurity, both defensive and offensive. And we'll continue to reference very recent news and stories like you see here. Let's start with what is machine learning and what is AI. People often conflict the two. Machine learning is pretty much about improving algorithm performance. In fact, there's a well-known machine learning book where the author says that machine learning is the process of taking a set of input vectors and over time improving your set of output vectors. Now, that doesn't sound near as cool or as exciting as some people would like it to be, but that's an honest review of what machine learning is. Artificial intelligence is a little bit more. We're wanting the system to be able to make decisions with some level of intelligence. That could be something like an expert system that is able to make professional level decisions on particular topics, all the way up to true artificial consciousness. Now, for those of you that are concerned about Skynet taking over or something of that nature, we're frankly nowhere near that. I'm not saying that there's no one investigating those areas. I've done a little research in that area myself. I am saying that we're not even in the neighborhood of having artificial consciousness. And in fact, if you look at the complexity of mammalian brains compared to the current complexity we have in computer systems, we don't even have the level of complexity to make it happen. So I wouldn't be too concerned about that. However, actual machine learning is a real day-to-day part of probably all of your lives. When we're talking about simply being able to improve performance, one of the classic examples, and if you've ever taken a machine learning course at a university, you've probably programmed this example, is being able to recognize birds from pictures. You take a set of features, feather color, beak shape, those sorts of things, and try to get an algorithm that can accurately identify the birds. Well, that sort of machine learning is frankly everywhere. We're seeing smart cars, we're seeing machine learning algorithms that are better at diagnosing tumors from imagery than trained oncologists. There's been multiple studies that show that. I'm currently working on a study which is identifying brain states from EEGs using machine learning. Is the person confused? Is the person upset? That sort of thing. This sort of thing is day to day, and I'm guessing, given the number of attendees I see here, a lot of you have actually done machine learning programming. Anyone who can download Python and TensorFlow can be off to the races. So this is very, very real. Now, another issue is the difference between expert systems and various data science systems. What we're looking at an expert system is the ability to automate decision making. Can the system not just identify something, but make a decision? I got the opportunity to watch a demonstration at a conference in Beijing just before the pandemic, where one of the researchers had used machine learning with a robot to get it to identify a target and then follow the target even when there were attempts to obfuscate the view. In other words, they picked a student on campus. The robot identifies the student and tries to follow the student around campus. But they try to interfere, like have people of similar build and similar clothing go between the student and the robot, use a fog machine, use different lighting, and it was still able to track the appropriate student and not get distracted. That's more of an expert system. We're seeing more and more of that all the time. Now, decision support systems are simply trying to gain knowledge. We talk about things like data science and data mining. The concept is to make sure we have data that a human expert can utilize to make a decision, as opposed to an expert system where it itself is making a decision. Often decision support systems work in a very unstructured environment, and they may not know all the alternatives that can be used. So we have two different ways of applying a little higher level of AI. Now, when we talk about machine learning, there are four basic classes, and most of it comes down to the first two, supervised or unsupervised. Supervised simply means I know what my goal is. To use a cybersecurity example, I would like to detect spyware. I know exactly what the goal is. I have a training set of known spyware, which I can train on. Unsupervised allows the system to just go through data and categorize it, and we're not sure what it will find. That's more related to things such as data mining. Now, we have semi-supervised, which is somewhere in between the two, and reinforcement learning, where just over time, we essentially reward the system for getting it right. A lot of different approaches, and I'm not simply going to read slides to you. We're not going to do death by PowerPoint, but I do want you to realize there's a lot of different ways to think about learning. Are we going to do statistics? Are we going to do supervised or unsupervised? Do we have evolutionary learning? Are we using basic logic? What are we doing in there to make the system learn? Now, regardless of how you approach it, you have a process that's essentially the same with every machine learning project. Collect some data and prepare it for analysis. That means putting it in the right format, picking the right elements to analyze, that sort of thing. Feature selection. What features do you want to analyze in order to make your determination? Let's go back to our example where we're trying to identify spyware. Well, what makes something spyware? You might look for software that takes a screenshot. You might look for software that intercepts the keyboard process. You might look for software that writes to specific registry keys, things of that. What features are important to you? Then you pick an algorithm. Now, there are more algorithms than you could possibly list during the space of time we have here. Different ones have different purposes. I've sometimes been asked, what is my favorite algorithm? I believe that's kind of like asking a carpenter what's their favorite tool. Depends on what they're doing. In this situation, I might like a hacksaw. In another situation, I might like a bandsaw. Then you select your parameters and models, run your algorithm, and evaluate. How well did it do? Now, probably the most well-known thing in machine learning are artificial neural networks. We have nodes that represent neurons and connections that represent synapses. A lot of people really like artificial neural networks because to some degree they emulate biological brains. So it seems logical that this would take us closer to realizing actual machine intelligence. Now, a lot of this is based on a concept from 1943. McCulloch and Pitts came up with the concept of a biological neuron. Basically, I have a set of weighted inputs, and if all those together meet a certain threshold, then we fire and we send a signal to the next layer. That's pretty much how your brain works. And this is how all neural networks and all the various variations we'll see function. And normally the reason we're going through layers is because each layer gets a little closer. In this case, we just detect general features. Then we try to group them together. And then the next layer will try to give us high-level objects of a face. And this is essentially how a neural network functions. And in general, we go with this concept, Hebb's rule. Now you see it written out formally here, but it's often colloquially phrased like this. Neurons that fire together, wire together. In other words, when two nodes routinely fire together, the connection between them becomes stronger. And neural networks will do that. They'll start making the connection between two nodes stronger and stronger based on the fact that they fire together. Now, I mentioned before there are so many variations of different algorithms. If we just focus on neural network variations, there are dozens. And I'd like to show you a few here. Each of these were designed by some researcher to accomplish some particular goal. Some of these are really good at one item and others are good at a different item. So we have to keep in mind what we're trying to accomplish. But you can see recurrent neural networks, feed-forward networks, autoencoders, and there are several variations of autoencoders. Then we have Boltzmann machines and several variations on that, convolutional networks, deep convolutional networks, deconvolutional networks. We move ahead to generative adversarial networks, liquid state machines, neural Turing machines, and there are just so many variations. And that's kind of important because I'm certain that some of you probably already are working in machine learning, others wish to. So a lot of algorithms to learn. Don't be too overwhelmed. It's, again, like the tools in a carpenter's toolbox. Each one has its purpose. Now, I mentioned before we have supervised machine learning, where we have a specific goal. We know what we want the algorithm to do. We know what success looks like. Then we have unsupervised. Now, neural networks are supervised algorithms, but what is unsupervised for? To me, that's the most exciting area of machine learning because it takes us to data mining. Now, a lot of people misunderstand data mining, and in fact, I would go so far without naming names as to say some university data mining programs don't seem to understand what data mining means. Data mining is not just using statistics and SQL queries. No matter how advanced your statistics, no matter how advanced your knowledge of structured query language, the most you can do is get answers to questions you knew to ask. Now, that may sound a little odd, so allow me to explain. True data mining uses machine learning to look for patterns in the data that we did not know to ask about. We didn't think to ask them. We didn't know that pattern was there. We just told our algorithm, please go out, analyze the data, and tell me what patterns you find. Now, anytime I talk about this, I repeat the same story because it's what got me excited about data mining and machine learning. It was over 20 years ago, I read an article where a recording company had decided to use a consulting company to do machine learning on their marketing data, hoping to find new avenues of marketing. Now, when the algorithm ran its course, everyone, including the vendor, thought there was an error because what their algorithm told them was that there was a spike in sales of rap music to senior citizens. And everyone thought, well, this has got to be an error. Well, when they analyzed deeper, what they discovered was a correlation between A, senior citizens who had grandchildren, and B, purchases near holidays such as Christmas. And then it was obvious. These senior citizens were buying rap music for their grandchildren. Now, I would have never thought to have asked the question, how many senior citizens buy rap music? But data mining gave us an answer to a question we didn't ask. And I think everyone sitting here today can immediately see applications of that to cybersecurity. Many of you work in cybersecurity now. You're in SOCs, things of that nature. Think about the sheer volume of log data you collect. Security information event monitors, SIEMs, collect logs from all over your network. You could have terabytes of log data. Now, you can go search it for specific items, but what's lurking in there that you don't even know about? Are there patterns that would indicate an imminent attack, an insider exfiltrating data? We don't know. And that's an area I want to address immediately. I do not see widespread, or at least widespread enough, application of data mining to cybersecurity. And we have tons of data. Every one of you probably knows just how huge logs gets. And reviewing a log manually, first of all, is a horrible, horrible idea. And even searching for specific things is only going to give you limited results. Now, to do data mining, you first of all have to identify the data. Go get it. Gather it up. And frankly, the more the better. You don't want to limit your data in any way. The more data you can accumulate, the better you are. It has to be in a common format, particularly when you're collecting data from multiple logs from different systems all over your network. Then you start the data mining. It's usually going to use clustering algorithms, unsupervised machine learning algorithms. What did we learn? Now, some of the patterns will come up and may not be meaningful, others will. Now, what can we do about it? That's the essence of data mining. Now, we're almost to the point where we're going to jump into pure cybersecurity applications. We have one more topic, and this is very applicable to machine learning. Things aren't always true or false. This brings us to what is colloquially called fuzzy logic, but is probably more mathematically called non-binary logic. Now, a lot of people misunderstand this, and fuzzy logic being integrated with machine learning is not new, but understanding why is not something everyone knows. The concept is very simple. We're not talking about the percentage to which something might meet some classification. We're talking about things that don't have a specific fine line. Is 90 degrees warm? Well, if you're sitting in a large conference and it's 90 degrees in the conference room, I'd say that's incredibly warm. On the other hand, if you're standing in Arizona in July, I'd say that's a nice, cool, brisk day. Is 90 degrees warm? Is there a specific temperature at which we say it wasn't warm now, but it is at this degree? Height is another common example. How tall is tall? Obviously, Shaquille O'Neal is very tall and Danny DeVito is not. However, is there a magic point? At 5'10", you're not tall. At 5'11", you're tall? No, we have degrees of tallness. And that's where non-Boolean, non-binary fuzzy logic comes in. It's not at a specific point we cross a line. It's our degree of membership. Now, when you're talking about identifying threats, now this part's just my opinion. This is my opinion, not necessarily widely held. But if we're going to identify threats, yes, some are very obvious. That's clearly a virus. That's clearly spyware. That's clearly a DDoS. Yes. But when we start talking about nation state attacks, these are going to be more subtle. They're not going to be the blatant kick in the door, alarm bells go off, yes, we have an issue. That's where fuzzy logic must be implemented. How much does this file look like spyware? It might look a little bit, which means we don't block it, we don't remove it, but we tell someone to go take a peek at it, maybe to take it and reverse engineer it. We have multiple incidents, the most famous being Mandiant discovering advanced persistent threats many years ago, residing on highly technical, including defense contractor companies for as much as several years with no one noticing them. In my opinion, the only way we're going to find those is fuzzy logic machine learning. Not just machine learning, but machine learning with fuzzy logic. Because when a nation state develops spyware, it's not going to be obvious. Now that we have this background on basic machine learning, data mining, and fuzzy logic, let's turn our attention to just looking at the cybersecurity applications. And we're going to start with defensive. Obviously, we could use machine learning, and systems do now, for intrusion detection or prevention, for antivirus. We can also use it, and I just mentioned data mining for log analysis and forensic investigation. And I'm certain we have some forensic analysts on the conference right now. And you all know that particularly if you're investigating a network intrusion and the network has 3,000 machines, how you decide even which machines to image and analyze, how you extract data from the log is a Herculean task. Data mining can assist us with that. Now, there are some things that machine learning does well, some things it doesn't. Things it does well: response time. Obviously, a computer can respond faster than you or I. Threat alert fatigue, and even though we're not in the room together, I can imagine some of the SOC analysts nodding their head right now. You get so many false positives that after a while you start ignoring them. I've investigated 8 false positives in the past 2 hours. This 9th one I'll get to after I go have coffee and a donut. And that 9th one may unfortunately be the one you should have paid attention to. It's not a false positive. Machines don't get fatigued. Human error in configuration. We all make mistakes, and myself absolutely as much as anyone else. Machines only make a mistake once. If we configure them right, they'll never make it again. A human being may do the same thing right 50 times in a row and mess it up the 51st time. One application I'm already seeing machine learning being used for is crowdsourced threat detection. You are all very, very familiar with sites like ThreatCrowd and things like that, where we can, any of us, submit a potential threat. But there's a problem with that. Anybody can submit it. I could simply not like you. I'm a competitor, so I start using different identities to submit your website as a possible phishing site just to get it flagged. That has happened. Well, if we add machine learning to analyze the crowdsourced threat detection, then it can look for various patterns to determine if this is a legitimate threat report, or perhaps it's one we shouldn't take so seriously. So machine learning can even improve crowdsourced threat detection. You're going to get a lot faster analysis. And in the case of logs and SIEM, frankly, there's really no effective way to do that without some level of machine learning. Some of you may disagree, but I'll stand by that. Your security orchestration, automation, and response, how we respond to things, is going to be much more rapid, and it's going to be mediated faster with machine learning. With intrusion detection systems, obviously, every antivirus, every intrusion detection system has a signature list that it can match to, but signature-based detection is limited. Obviously, it can only detect things we know about. And if there's a zero-day exploit, if there's a polymorphic virus that may have changed its format in some way, signature-based will never see it. Having some level of machine learning. Right now, almost all IDS of any worth at all at least do a statistical anomaly detection. But if we can add additional machine learning algorithms so that it learns over time and it gets better, and that's the whole clue. I put in a machine learning IDS system. It's not doing its best work today. It's doing its best work 3 months from now when it's learned. Now, that doesn't mean that it initially starts off failing. It starts off with the signature detection, the statistical anomaly detection. But as time goes on, if it misses something, it learns from that. If it miscategorizes legitimate traffic as an attack, it learns from that. So it will be better 3 months from now than it is today. And that clearly is the primary advantage of machine learning over any other approach. No matter how sophisticated your IDS is, it's only as good as you've configured it, and it's not going to get any better unless you develop new rules and add them. With machine learning, it's going to get better on its own. Now, antivirus and machine learning, there's a lot of products out there that discuss having antivirus involved, having machine learning involved in antivirus. I'm always skeptical of just how much machine learning really is involved because it's difficult to trust marketing literature. And I'm not disparaging any of these companies, and there are other companies that have the same marketing. I'm just saying that if you're going to select an antivirus based on machine learning, you need to know enough machine learning to ask some probing questions and find out what they're really doing. But let's assume they are. Where's the machine learning engine? In the cloud, locally? There are advantages to both. But for example, real machine learning, as some of you know, and the rest of you I imagine can guess, is computationally intensive. So if I'm running it locally, that's going to be a drain on my resources. Offloading it to a cloud resource might be better. Of course, if I have connectivity issues, that cloud resource is unavailable. So there are advantages and disadvantages. Several products are out there right now. IBM QRadar is an SIEM that also utilizes machine learning. IBM's Watson is their AI platform that they use. They have combined QRadar with Watson. Zscaler has advocated machine learning for zero-day exploit protection for quite some time. Now, a little more cutting edge. In 2019, I supervised a doctoral student who successfully defended his dissertation on a deep learning approach to detecting covert channels in the domain name system. His name is now Dr. Thomas Pena, who's a fantastic student. And let me explain a little bit about what he did. A sophisticated nation-state actor that has, say, spyware in your system is going to exfiltrate data subtly. And one of my favorite techniques that he locked on to before I even mentioned it was my favorite technique, if I want to exfiltrate data, what I'll do is exfiltrate it in very small segments. Each segment appears to be a DNS request. And I hide the data in what looks like a signature at the end of the DNS request, but it's not really a signature, it's the encrypted data I'm sending out. Now, on the one hand, that limits me to small amounts of data that I can exfiltrate at a time. On the other hand, no one thinks it's unusual to see multiple DNS requests going out of a system. Every time you go to visit some website, there's a DNS request. Well, what he did is use deep learning to analyze the DNS request, and he was able to successfully identify those requests that were actually data exfiltration. Now, that's some seriously cutting-edge stuff. I would mention that Dr. Pena was a retired Air Force colonel who had worked in cybercom for a long time, so his knowledge of cybersecurity and nation-state threat actors was pretty detailed. But that was some really great cutting-edge research, and there's more happening in that area all the time. Data mining for intrusion detection. Now, data mining doesn't happen live as we're doing it now. Data mining happens later when we're analyzing our data from past logs and things of that nature. But it can detect past intrusions, past scans, or someone doing vulnerability scans and things of that nature on our system. That sort of thing, data mining can go back and find out. Any talented hacker who breaks into your system was doing reconnaissance quite a while before they ever jumped in. Even if you miss the attack, can you go back and learn from the precursors that gave you that information? Can you learn from that and move forward? And I apologize if you're hearing some noise outside. I hope it will end very soon. This is one of the downsides of doing everything remotely. Intrusion detection systems are usually looking into anomalies or misuse, but we can capture all activities and data mine them. Another interesting application of machine learning in cybersecurity has been natural language processing. Can we look at language that indicates malicious activity, phishing emails, data leakage, fraud? There's been some success in this area, and I expect to see it improve. We're already seeing natural language processing to identify spam. Machine learning can also simply automate common things like patch management and vulnerability scans. And I believe everyone attending this right now is very well aware that such elementary, not very exciting things as patch management are probably one of the biggest challenges in all of cybersecurity. We love the exciting quantum computing, machine learning, and all that, but if we could just get everyone to apply the patches, we'd be in a better position. We're even seeing research on machine learning for digital forensics. Magnet Forensics touts artificial intelligence for analysis, specifically in child exploitation. Springer Press has some publications on this issue. Access Data, the makers of Forensics Toolkit, have a complete lab which manages investigations. Now, part of that is not AI for the investigation itself, for analyzing the evidence, but an AI assistant to help the examiner to make sure they've accomplished all their tasks, they're moving forward appropriately, that sort of thing. Now, we're going to talk about offensive purposes in just a moment. That's not the same thing as adversarial machine learning. Adversarial machine learning is someone trying to trick your machine learning. Obviously, as the good guys start using more machine learning for defensive purposes, the bad guys will seek to attack it. So using different terms to circumvent spam filters, the more they understand your algorithms and your approach, the more they might be able to circumvent it. Now, there's already some things out there you can use right now. Password cracking with generational adversarial networks. This was published by the Stevens Institute of Technology, and you can go read articles on it and actually download the actual code and use Passgan to try to crack passwords. Now, they were able to crack 47% of passwords in their test. That's pretty good. This is something you might want to look into. Even from a defensive perspective, you should try to crack your organization's passwords before someone else does. Just a few weeks ago, we had an article published where an AI system was used to actually write phishing emails, and it wrote better phishing emails than most humans. I'm sure you've all been amused by the phishing emails that were so painfully obvious you had to wonder who in the world fell for this. Well, again, the bad guys can use machine learning just like the good guys, and they can start writing better and better phishing emails and do it automated. Now back to Passgan, you can see it's a simple Python script. You do your install requirements and you're off to the races, and you're ready to use Passgan on your own password data sets. Now we're going to switch gears a little bit more and go deeper into specific offensive cyber warfare modalities. How do the bad guys, be they individual hackers or nation states, use machine learning? Well, smart botnets, often called hive nets or swarm bots that are self-learning, are a lot more effective than a traditional botnet. We already know that machine learning can write code. You've all probably seen articles. Well, that enables us to have truly polymorphic and metamorphic malware, which has been mostly theoretical for a long time, but it can be very much a reality now. This year has set records for zero-day attacks. Well, if you can use machine learning to identify vulnerabilities, so can the bad guy. If you're looking for zero-day vulnerabilities, machine learning presents an excellent way to do that. And again, this is a very recent article, just 2 weeks ago. I also think about machine learning in the context of cyber warfare. The bottom line is we can all see weaponized malware, and there's some examples here on the screen that you're probably all familiar with, is a part of modern cyber warfare. Machine learning obviously must be a part of that. August 2019, we have a general discussion of AI and automated phishing. 2018 predicts hackers using AI, and I think that prediction is probably a little late for the game. 2019, they're predicting increasing use of AI in attacks, and we're going to see more and more AI. It will start with the sophisticated nation-state attackers, but work its way to everyone. Now, when we talk about using it in cyber warfare, the bottom line is this. Nation-states have conflicts. Sometimes they use what's euphemistically called kinetic weapons. Sometimes they use cyber weapons. Cyber warfare is a reality. It's going to happen. Machine learning can certainly be a portion of that. Now, this is a nice definition of cyber warfare. It involves the actions by a nation state or international organization to attack and attempt to damage another nation's computer information networks, for example, through computer viruses or denial of service attacks. Now, all of these are various examples of famously known weaponized malware that was used by one or another nation state. Given our brevity of time here, I won't detail each of these, but if you're not already familiar, you can certainly search for them and find out details. Now, weaponized malware does require actual engineering. In my opinion, and we don't have the time to go into detail right now on it, but I've actually published papers where I think things like Stuxnet were an operational failure because they weren't well engineered. They were easily discovered and didn't achieve their goals. So if we integrate machine learning into the systems development lifecycle of weaponized malware, we can do a few things. Make it work better, but also improve target discrimination, reduce collateral damage. One of the reasons I think Stuxnet was a failure is it hit millions of machines that it wasn't intended to hit. So what I'm saying is incorporating machine learning into the development of weaponized malware could reduce collateral damage and hit the targets you're after. For example, using artificial neural networks for training, Stuxnet targeted Siemens Step 7 software for a Windows machine. If you want to use something like that, set up a virtual system that has both targets and non-targets, and have the software learn to discriminate between what is a target and what is not before you release it in the wild. So you're no longer hitting innocent targets and you are hitting your preferred target. Using decision trees to see whether or not countermeasures will detect you. And again, this is in a training environment. I set up my malware, and let's say it has to read a registry key. I'm going to see whether or not that triggers an antivirus. So I wait 2 seconds, read another key. And I'm doing this in a training environment till I find the optimum pace of activity that's least likely to trigger antivirus, intrusion detection system, things of that nature. Naive Bayes algorithms is a natural fit for training because we're looking at probability. And I'm looking at my time. I realize I'm running a little short here. K-nearest neighbor is another method for classification. Fantastic for improving target acquisition. So we can create a composite methodology where we have virtualized training environments where we train the weaponized malware for specific mission goals. You can even use machine learning in deployed malware. Now, I've had people say that's not possible because machine learning is computationally intensive, and if the deployed malware, say spyware, is running machine learning algorithms, it will have an impact on the target machine, the victim machine's performance, and be detected. Well, you're exactly right. So what I suggest is your deployed malware is just slowly leaking information back to a command and control server. That command and control server is running analyses using machine learning. In other words, let's say I'm a nation state and I'm trying to spy on another nation state. And I've sent out 20,000 instances of spyware. Each one of those is going to send back little bits of information to a command and control server, and all the aggregate data can be analyzed with machine learning. When a particular node goes offline, we can look and say, was it likely detected or did the computer turn off? If it was detected, what was the information we got from it just prior to detection? Okay, now we get some idea of how people detect our spyware, and our next iteration of spyware would be more robust. So I'm talking about offloading the machine learning to a central command and control server, and at that point you have deployed machine learning malware. But beyond cyber warfare, machine learning has lots of applications in traditional defense, and these are all fairly recent articles. The Air Force is looking at artificial intelligence for electronic warfare. RAND organization is looking for AI just for military readiness, for training, for weapons development. Think about how much money is wasted when you send someone to some training school that they can't succeed in. Famously, Navy SEALs BUDS. The dropout rate from that is huge. And we all think that's great. That shows how elite they are, and that's wonderful. I'm not suggesting they lower their standard. But every student you send to that class who fails was a waste of time and money. Could we use machine learning to analyze the records of those who succeed versus those who fail, and maybe do better at sending people that are likely to succeed? Raytheon is developing all sorts of AI systems to work in all sorts of machine learning environments. Now, before I open the door to questions, there's one last thing I always like to address when I talk about machine learning. I get this question emailed to me all the time. What do I need to know to do machine learning? Well, you could download Python and install it. You could install TensorFlow, and you could probably download a few algorithms and get them to working without understanding them. But without some understanding, you're terribly limited. You must have at least one programming language that you know well. It doesn't have to be Python. In fact, TensorFlow comes for just about every language you can imagine. But Python, you're going to find the most example scripts out on the internet. You're going to have to know some basic statistics. I'm not saying you have to be a mathematician, but a lot of machine learning involves, we mentioned naive Bayes classifying before. If you don't know Bayesian statistics, you're going to have a difficult time with that. And unfortunately, there is some math involved. The most important math in machine learning is linear algebra. And it's okay if you didn't take linear algebra in college. I know the Khan Academy has a free linear algebra course. There's a great book out. I normally don't like the For Dummies or Demystified series. I think they're overly dumbed down, but Linear Algebra Demystified is a great book for a novice to learn linear algebra. Now, when I talk about cybersecurity for defense purposes, what further work do I envision? Working with more algorithms, machine learning versus machine learning and training, better modeling, all of these. Now, I realize I'm down to 5 minutes left in my talk, so this is an excellent time that I'm going to stop sharing and just get ready to answer questions. And I understand I'm about to have some questions sent to me in the chat room. So if you have questions, now is the time. I always get this question. What is on the monitor in my background? Well, that's Skynet preparing to launch. So I really hope you enjoy the conference today, because this could be the end of civilization. No, it's actually simply a screensaver. And I get that question all the time. In fact, I forgot I had it on during an actual court hearing. I work as an expert witness frequently. And the judge finally stopped and said, Dr. Easton, what's going on behind you? And that was a little embarrassing. Next question. Given how inhibiting computational requirements are with machine learning, it seems something like Stuxnet with machine learning is not obvious at the moment. Well, again, in putting the machine learning actually in the deployed malware, you're right, simply is not a plausible solution. But having malware that slowly leaks small bits of data offline to a system that there at that offline system is doing the machine learning, that's incredibly realistic. So you're correct, we cannot do the machine learning on the victim system without being detected. Someone is asking, which knowledge is necessary to be a cybersecurity data scientist? Well, if we're going a little further into data science, I'm going to say a few things. One, more advanced knowledge of statistics is necessary. I would say some knowledge of information theory is going to be helpful. Now, the good news is educational opportunities today are abound. And once upon a time, machine learning was frowned upon. But first of all, machine learning today is widespread. Harvard does machine learning. MIT does machine learning. Oxford does machine learning. You can't say machine learning is not real. Second issue is COVID-19 has taught us we have to do things by distance learning. Excuse me, distance learning, not machine learning. I'm getting myself distracted. So you can do data science study by remote. There are all kinds of certificates. There are master's degrees, all kinds of things you might use. So to be a data scientist, you're going to have to learn some math. Someone is asking for the links. I don't have a link to the Khan Academy, but I think if you just Google Khan Academy, linear algebra, you're going to find it. As far as the links in my presentation, anyone who emails me, I'll send you a copy of the presentation. You can have all the links. So I've caught up with questions so far. Do we have other questions? Okay. This is an interesting one. What are your thoughts on using AI or machine learning to detect AI or machine learning based adversarial attacks? Well, I think that's a fantastic idea, and I really think that's about the only way we're going to detect those things. Frankly, if you have well-developed machine learning attacks, it's highly unlikely that a non-machine learning source is going to be able to detect that level of subtlety. So we're going to get into essentially, and it's already starting, an arms race between the good guys and the bad guys, each side improving their machine learning and each side getting progressively better at it. And eventually, we don't know where this is going to head, but we definitely have an arms race. Now, someone else is asking, how well is machine learning at detecting and decrypting ransomware? Well, if the ransomware is done properly, and I mean they properly implemented the cryptography, it's probably not going to be that terribly effective at decrypting it, because the whole idea of good cryptography is it's based on mathematical problems that are simply computationally difficult to solve, even by a machine learning algorithm. So I don't see machine learning as doing well at decrypting ransomware. Normally detecting is not hard because the ransomware tells you your files have been encrypted. Please give us some money. Now, I'm told this is the last question. If you have other questions after this, certainly feel free to email me. I'll respond as soon as I can. But this question is, suppose we believe we've got a machine learning running. Is there a way to see which model is in use by the system? Do the different models have different signatures? Well, I'm assuming you mean you believe you're under attack from a machine learning adversarial system. There's really no way to tell from the output what the nature of the system is. Now, if you actually have a Python script running and you can see what's coming out to the screen, well, yes, that would tell you what sort of algorithm is being run. But if I just have a system attacking me, I can't tell you from that whether it's using a convolutional neural network, a deep belief network, or what have you, unfortunately. So I'm told that was my last question. We do have to make room for the next speaker. I really appreciate your time attentiveness this morning. And there were some really great questions, which is the most important part to me, because I already knew the presentation. Your questions were interesting to me. So thank you very much for your time. And again, feel free to reach out to me via email, social media, what have you.